A skydiver jumps out of an airplane with an initial vertical velocity of 0. They then fall straight downwards. They experience a drag force that is proportional to their velocity. And there's an equation given where k is a constant. What is the terminal velocity of the skydiver? This is the point at which they are no longer accelerating. Using Newton's second law, create a differential equation that could be solved to find a relationship between the velocity and the time. Now, a few of you should be able to do the last part, but I don't expect the last part to be something all of you can do. So let's talk about the beginning of this question. So the skydiver jumps out of the airplane, and it says that they have an initial vertical velocity of 0. We're also told that they are going to experience a drag force that is proportional to the velocity. Now, there's more to this than that. They say that the direction of this force opposes the velocity. The value of k is a constant, so it's a scalar. V has a direction, and this is a vector equation, so the negative sign here is about the direction of that force. I just want to make sure we don't do something kind of like inexperienced, which could be just to blindly put the negative sign into some equation. This negative sign is indicating what direction the drag force will be, and it will always oppose the direction of the velocity. So it's not about necessarily the force being negative. I'll point out if it was a ball that was hit, like from a bat, and its velocity off the bat was this way, that equation is telling you that the drag force would be this way. It opposes the direction of the velocity. So make sure you read this equation correctly. Now, at time 0, the velocity is 0, so the drag force is 0. That has to be true. So the moment they jump out of the airplane, they're experiencing no force of drag because they haven't started moving yet. So their free body diagram at t equals 0. So I'm being very careful. This is at t equals 0. Their free body diagram has a single force, mg. So at t equals 0, the net force will equal ma. That net force is just their weight, so the force is clearly unbalanced, and they accelerate. Just throw that anywhere. Now, the fact that they're accelerating means their velocity is going to change. In this case, it looks like it's going to change with an increase in their velocity downwards. So after a few moments, they are certainly moving downwards with some velocity. This is no longer t equals 0. This is t equals some time in the future. Their weight will not have changed. But now they are moving, so they must be experiencing a drag force that is upwards equal to kv. This is sometime in the future. Now this means that their net force, which is still going to be equal to ma, is now going to have an acceleration that is different. Here, at time equals 0, their acceleration is equal to g because it's the only force they have. Over here, well, I'll have mg downwards minus kv upwards equal to ma. This highly suggests that the acceleration is less, right? Because ma equals mg minus something. So the net force is smaller. But the net force being smaller doesn't necessarily mean the acceleration is 0. It just means the acceleration isn't as much. So more time passes. Some new velocity in the future that is now greater than the velocity they had a moment ago. That suggests the weight downwards, still the same, and an upward force due to drag that has now increased. The net force is still going to equal ma, still mg minus kv equals ma, but now this velocity is bigger than this velocity, suggesting the acceleration is getting smaller. It's getting smaller as the velocity is getting bigger. So there's going to be an inevitable conclusion here. Eventually, we're going to reach a point where, although mg hasn't changed, the velocity has increased enough where the net force will equal 0. And that's the inevitable trend that's happening here. When we reach that point, this is what's known as terminal velocity, because it's not going to increase after this. After this point, the net force is 0. So there's no acceleration. And therefore, mg equals kv, suggesting that the terminal velocity will be equal to mg divided by k. This is after some time has passed. All right, so we start off with a net force equal to ma, and that velocity starts getting bigger and bigger and bigger in the other direction until the net force equals 0. And that's when we reach terminal velocity. Now, a thing to consider here is that when we look at what's happening here, the velocity is getting bigger. But it's not doing so the same way the whole time. The rate at which the velocity is changing is getting smaller, because on this side, the acceleration is decreasing. So with every moment that passes, the acceleration, the thing that's changing the velocity, is getting smaller, but the velocity is still increasing. This is feeding together until eventually we reach what's known as a steady state condition, where the net force equals 0. Now, that's how you answer the first part of number 1. And I don't know you had to do all of that. Knowing that the steady state condition is when net force equals 0 is probably important. If I was trying to think of things to put down in your notes, that would be one of them. That way we do question number 21, which is essentially the same question, but a different kind of drag where it's proportional to the velocity squared. You can do that. The fact that there's a proportionality constant, k, don't be alarmed by that. Drag is proportional to a whole bunch of things. We're just wrapping it all up and making it k. But there's lots of things that affect what k looks like. You don't have to worry about that. We're not getting into aerodynamics to know that some things are more aerodynamically balanced than others. That's not a part of this. Drag is generally proportional to velocity or proportional to velocity squared. There's a couple different kinds of drag. This is one of them. Now, that part I think is, I could have expected that from all of you. There's not a whole lot there. And there's enough there where maybe some of you were confused by it, but did you draw anything to maybe consider what was happening? And they were telling you in the problem, these were the things that were happening. So I think that part's reasonable. The next part might not be so reasonable. So I want to talk to you about the next part, where it might have been less reasonable for me to expect you guys to have made it through there. We had a chance to talk about this in 6th period, not so much in here. So when I go on, it says, using Newton's second law, create a differential equation that could be used to find a relationship between velocity and time. It is telling you what to do there. You probably just don't have the experience to do it. But let's see what it tells me to do. Using Newton's second law. All right, so I think we're talking about one of these, right? Because this is where we're in second law, and we have a drag force. At time equals 0, we don't, but here we do. So using Newton's second law. All right, and let's pick one of these, because this is the part that matters. Something about Newton's second law. So I'm going to pick something in the middle. Where I have mg downwards and kv upwards. Newton's second law says the net force equals ma. I'm going to do what Newton's second law says to do. Mg minus kv equals ma. Now here's where you need to be careful. They said we want a differential equation that could give us velocity as a function of time. We need to rate velocity and time together. I'll point out that our net force equation relates velocity and acceleration together. You guys see that pretty clearly? Doesn't talk about time. But you're supposed to bring stuff to the table, stuff we talked about in kinematics. And you know things about velocity and acceleration. You know that acceleration is related to velocity. In fact, you know that acceleration is the rate of change of velocity. You also know that velocity is the rate of change of position. Those are two things that you know. So you need to create a differential equation that could be used to find the velocity. You need to make a substitution. A substitution that puts a differential into our equation. Now, one of these makes sense and one of these doesn't. I can sub in velocity with dx dt, or I can sub in acceleration with dv dt. Again, one of these makes sense, one of these doesn't. And for those of you who are going to become good at this and proficient at this, and if you want a 5 on the exam, you'll have to. You have to realize that they wanted velocity as a function of time. If I sub in something here, I create an equation that has position and time related. It's probably going to be less helpful. If I sub in this one, I get something that will relate velocity and time, because acceleration is the rate of change of velocity with respect to time. So creating a differential equation is just substituting in a differential. These are the only two differentials you know. It's always going to be one of these. And I'm going to tell you a trick. In this class, it's always going to be a Newton's second law problem where you'll have to do this. So I would say more than 75% of the time, you're making this substitution. That is a differential equation. All you have to have a differential equation is an equation with a differential in it. That's all you have to have. And that's what we got there, an equation with a differential in it. Now, solving a differential equation is a whole nother thing. That's different work. And most of it is algebra, but one step of it is calculus. You will be expected to do all of the steps that are the algebra part. And then as the year goes on, as you guys get better at math, and after you've practiced that part enough, I'll expect you to do the calculus part. But every time we're faced with this, we're going to do the whole thing. So we're faced with it right now. We're going to do the whole thing. I'm going to tell you which steps I would commit to memory. They're steps. And I will tell you where we're doing calculus versus where we're doing algebra. And we've already done this. We did it for simple polynomial functions already. So you did this already. But this won't be a polynomial. This will be harder. So I'm going to go through the series of steps. But right now, this problem, I would expect you to be able to get to here on a test. And I'm okay with this, because there's nothing new to this point. It was just put together new in this way. Now, should you be able to do the rest of this, some of it might be worth a little extra credit on the test. So this might be worth, I don't know, writing some things down. That's up to you, I don't care. The process we're going to use is called splitting the differential. And although technically this is what we were doing way back in kinematics, we didn't do it. We didn't do this kind of pomp and circumstance. So the first part of all of this is just algebra. So you need to do some algebra. And the first step is to split the derivative, split the fraction. So to split the fraction, you just multiply by the denominator of the fraction. So the denominator is dt. So that's all you're going to do. Multiply both sides of the equation by dt. So from here to here, the demon of the fraction. I better not write demon. I'll say denominator. All right. The next step, you need to collect like terms. Now, this part is not terrible, but you're just going to be multiplying or dividing. You need anything that has a t in it on the same side as dt, and anything with a v in it on the same side as dv. Now, I will notice, and I hope you do too, that there is no t in the equation. So there's no way for me to get any t's onto any side because there are no t's. But I do see a v in the equation, do you? You can only do this by multiplying and dividing. You can't subtract because you'll still be left with dt multiplied by something over there. So you need to get this whole thing off this side because it's being subtracted. So you just divide both sides by the whole term. So I'll get dt all by itself on one side, and I'll have m over mg minus kv on the other side. I have collected like terms. Yep.
Does the dv stay out of the equation?
Yep.
Put it in the denominator?
Stays right where it is. That's where I would like it to stay. It doesn't matter if you put it on top of the fraction. It doesn't change the meaning of it. But the next step we're about to do is about to get us prepared to do calculus. So the way calculus looks has a certain symbology. Having the dv separated meets with that symbology. So the next step is setting us up to do calculus, but it isn't doing calculus. What we want to do is we want to set our limits, also known as applying boundary conditions. Now, this does involve putting a calculus symbol here, and it's the integration symbol. The integration symbol is just a fancy S, because it's just a different way of doing a summation. So instead of using sigma, we use the integration symbol. Now, putting the symbol there isn't setting our limits. We have to set our limits. The left side limit is about time. The right side limit is about velocity. The top of the integral is a symbol that you will use to represent the variable in the future. So I'm going to use a t to represent time in the future. And on the velocity side, I'm going to use v to represent velocity in the future. All you need is a symbol that you're going to use to represent that variable in the future. On the bottom, we put our boundary conditions. We were told in the problem that at time 0, the velocity was 0. That's a boundary condition. We are given the velocity at time 0. So we know v when t is 0. We put that into our boundaries. That's it. Without knowing calculus, this is as far as you can go. For those of you who are taking calculus, you'll learn how to do both sides of this. You won't learn how to make differential equations. Unless you're in BC. If you're in BC, you will. But if you're in this class and you want to finish this, you will have to learn how to do this. You already know how to do the left side, because the left side is a polynomial. You don't know how to do the right side. The right side's not a polynomial. So the left side, when we were taking the antiderivative and there was no number there, if you'll recall, you were told to put in a number to represent t to the 0 power. There's an implied 1 there. 1 times dt. You were supposed to know now, after this, what to do on the left side. And you should be able to. You should be able to apply the rules for finding the antiderivative of a polynomial, which meant adding 1 to the exponent and dividing by the new exponent. Sound familiar? Do you guys remember doing this? So the left side of this just becomes t, evaluated from 0 to t. That's all that is on the left side. The right side, well, that's a whole different thing. That's going to be a lot of work. And since most of you have had calculus, I don't want to scare you off. I'm not going to expect it on the test on Wednesday. I expect that you could get to maybe here for extra credit. I expect that you should be able to do this for regular credit. Do you understand each other? I have no trouble expecting this out of you. There was nothing really new there, just a substitution. But what happens from here? Well, that's a lot of work, and let's focus on tomorrow's or Wednesday's test. Let's not spend a lot of time on something I'm not going to expect yet. All right? So I believe that's everything for question number 20. That's within the expectations that I want. Yep.
Can you do question 3?
Probably.
Thank you.
3?
There's a lot of information here, and depending on where we start this problem will determine, the order of things to do. If the baseball player is running this way at 5 meters per second and suddenly begins their slide, assuming they're still traveling 5 meters per second at the moment they start their slide, and now for the next 10 meters, they slide until they're now going 2 meters per second. This to me looks like motion equation stuff. And I think we're assuming that it had some kind of uniform acceleration. The only way to do this. And since kinetic friction is a constant force, as long as the normal force is constant, this makes reasonable sense. So 5 meters per second, 2 meters per second, 10 meters. It seems to me that we could find acceleration or time with this information. Since force is all about acceleration, I would hope it wouldn't be too much of a stretch to expect you to get the acceleration from this. So I'm sure there's a reasonable relationship that would lead you to get the acceleration. At the same time, I think the player is experiencing 3 forces: a downward force of weight, an upward force normal, and a frictional force to the right. Any question about that? I think the forces are unbalanced, and that's good. So I'm going to make the positive direction the direction of the acceleration, which I think should be to the right, slowing the baseball player down. And that means the up and down direction will be the y direction. So net force in the y direction will equal 0, so normal equals weight. And net force in the x direction will equal ma, So friction equals MA. All good? Any questions yet? All righty. I know that friction equals mu times the normal force. So I think MA equals mu mg. Well, don't even need the mass of the baseball player. And I'm pretty sure I have a way to get the acceleration. I think that's it. U is going to be A over G. Just find out what the A was. Multiple choice. This is not a problem. This is an exercise. You guys get an idea? I expect this problem can probably be done in 1 to 2 minutes. I don't think it's unreasonable. And I think that's about the level you should be working at for something for this level of the test. So I would expect this on the test, but I would expect it a small piece of a larger FRQ or multiple choice. The string is 1.2 meters long, and the string makes an angle of 15 degrees with the horizontal while it's spinning. What is the linear speed of the ball, and what is the rotational speed of the ball in RPM? All right. So the string, 1.2 meters long, and is spinning above my head with in some kind of circular path. So I'm expecting a circular path. So I'm just trying to draw a picture. Something like that, and the ball is, say, here. And this is 15 degrees. All good? All right, let's start the problem out. I believe the ball is experiencing 2 forces, a tension force and weight. So I would say that there's weight this way, mg, and tension this way. I think the tension is going to be much greater than the weight, just based on that angle of 15 degrees. Based on this, I would want a coordinate system that's aligned with the horizontal, because that is the direction of the acceleration. Meaning I need to have an acceleration towards the center of the circle. So I'm going to make that the positive x direction, and that's the y direction, so this is positive x. I believe there will be a force of tension along this line. I think there will be t in the x direction, which will be t cosine 15, and then there will be a t sine 15 here. Any questions yet? Quick look at this suggests that t sine 15 minus mg equals 0, and t cosine 15 equals mac. I skipped a step or two, but I think I'm okay doing that at this point. Let's go ahead and solve this for t sine 15 and get t sine 15 equals mg. If I just divide these two equations, I'm going to cancel out t and m. And I know the acceleration is what I'm really after, because the acceleration has got v in it. You guys good to see what I'm doing? So let's divide these two. We'll get tangent 15 on the left and g over ac on the right. Any questions? I'm just trying to be efficient. Yep, go ahead.
Oh, sorry, never mind.
Are you sure?
Yeah. Jaden just explained it.
All righty. I know that AC has got the velocity buried in it, so I'm going to solve this for AC and get AC equals g over tan 15. And that's going to be v squared over r equals g over tangent 15. I do need r before I proceed, but I'm going to go ahead and multiply both sides and get v squared equals gr over tangent 15. I need r, though. It wasn't given to me in the problem. So let's go up there and see if there's some clues. I know the length of the string is 1.2 meters long. And if the length of the string is 1.2 meters long, then won't this distance from here to, come on, from here to here be based on the angle and the length of the string? Because that's going to be the radius. So I think this radius is going to be 1.2 meters long times the cosine of 15 degrees. It's got to be the radius of my circle. We did this in class, right? A couple weeks ago, 2 weeks ago. Just making sure. So it looks good to me. So I'm going to, down here, say this is equal to 10 times 1.2 cosine 15 divided by tan 15. That'll give me the velocity. We're going to need that to do the next part, so if you want to type that in and all and get an answer, I'm down. And if I beat you guys, I'll be mad. Well, I've got an answer. Didn't take the square root yet, though. All right, I have my answer. Hope somebody else gets the same one as me. I have 6.6 meters per second. Anybody else get that? Did? All right. I would leave some decimal places in there, but I'm just going to write 6.6 meters per second. Go ahead, Kendall.
I just have a question. Did you have to use tangent, or could you just do t equals mg over sine of theta and then just like plug it in that way? Because I got the same answer, not like that would work every single time.
You got, I'm sorry, say all of what you asked again.
Like, did you have to do tangent of 15? Because what I did was I solved for t equals mg over sine of theta, and then I plugged that in. And then I had gr cosine of theta over sine of theta equals v squared. But I got the same answer.
Well, yeah, because the tan there
Oh, never mind, yeah.
you would get the same thing. It's algebraically the same. All right, so we're close to the end here. We're not quite done. It wants the final velocity of the rotational speed of the ball in RPM. We have the linear speed of the ball, and the linear speed of the ball is 6.6. So considering that it's traveling in a circle, the radius of this circle is 1.2 cosine 15, and it's got a velocity like that. We could say velocity equals omega times r. By doing this, we have a way of figuring out the angular speed. So that'll be 6.6 divided by 1.2 cosine 15 equals omega. How are we doing over here, guys? You want to ask a question or just keep talking amongst yourselves and answer each other's questions? I'm good either way, but I'll stop talking so that you guys can be heard. And I'll just keep writing. You just what?
I get it.
Well, we'll know on Wednesday, right?
I guess so.
I know, but I'd get your questions answered, and if she's doing a good job answering them, I'm down.
I think it's it.
Okay. The top is in meters per second, the bottom's in meters. So this is going to give me a value that's in radians per second. So when I do that, I get 4.5. I think it's 4.5. 4.54 radians per second. That will have to be converted to rotations per minute. If you guys are good at doing that, then I don't have anything more to do. Just make sure you convert your answer. If you guys need to see that done, you should ask, because, what's that? All right. 4.54 radians per second. I think you should use unit multipliers if you're not good at this, because it's hard to make mistakes. If you make a mistake on this, it's a silly mistake and you lose the 1 or 2 points. So to use unit multipliers, put your target down and give yourself some space. My target is revolutions per minute. That's my target. I want to go from radians per second to my target of revolutions per minute. I'm going to use unit multipliers, which means I'm going to use a multiplier that will convert one thing at a time. For example, I know a unit conversion to go from seconds to minutes. So I'm going to multiply by something that will convert this from seconds to minutes. If I had to go from like seconds to days, I might have to do that 2 or 3 times because I may not know a direct conversion. Does that make sense? But I do know that I'm going to have to convert seconds to minutes, and I know a conversion for that. So I'm going to put a parenthesis with a fraction in there. In my head, I know I'm setting that one up for minutes to seconds or seconds to minutes. And I'm going to have to do another one to get from radians to revolutions. Now, just need to pick one to convert first. So let's pick the radians. To convert radians to revolutions, the first thing I realize is radians is in the numerator. So in my multiplier, I put it in the denominator. I want the radians to cancel. And I want to be left with revolutions. Since I know a direct conversion, I only have to do this once, but I need to know my conversion fact. And my conversion fact is that for every 1 revolution, there are 2 pi radians. My next conversion fact is to go from seconds to minutes. I want to cancel seconds, and seconds are in the denominator. So I'm going to put seconds in the numerator so the seconds cancel. And I want to be left with minutes, and I want those left in the denominator. So that works out just as I expect. But I'm going to need a conversion fact. My conversion fact is that for every 1 minute, there is 60 seconds. Now all I have to do is multiply the top across and multiply the bottom across, and whatever I get is my answer. Now, look, you guys will say something like, look, I just multiplied by 100 when I should have divided by 100 or some garbage like that, and expect that you'll get your point back. You won't. In fact, I'll even take a point for making that argument because it's not hard to know whether you need to multiply or divide by whatever your conversion fact is if you write it out. If you're just trying to do it in your head because you think you're smart enough to do so, you have a lot of stuff you have to keep in your head. You may want to write something out. So, I'm almost done here, but 2 has a question.
So is this going to be always like, when you convert, it's going to like always be like that? When like revolution over rad and then second over minute?
Not unless I ask for revolutions per hours or revolutions per days, or it could be any number of things. I could ask for degrees per second. You know, it's whatever your conversion is going to be.
So like, if let's say you have like radian per second to like hours, so how do you like do the middle part?
I would need to then go from minutes to hours. I would have to add another conversion there, right? Because I don't think I know how many seconds there are in an hour, so I might have to do 2 conversions. All right, so multiply the top by 60 and divide by 2 pi. I got like 43 RPM. All right. This is more than an exercise, but this was a largely procedural question. So this is fair enough to be on a multiple choice, but I think it'd probably be more appropriate in FRQ because of the number of steps necessary. I think a portion of it could be on the multiple choice. All right. Anything else on the homework? Go ahead. No one else has a hand up? Sure. You kind of did this one. An object of mass m is sliding across a level floor where it is experiencing a drag force that's proportional to the velocity, where the drag force is proportional to kv squared, where k is some constant. There's no frictional force. The speed of the block is v naught at time 0. Create a differential equation that could be used to determine the velocity of the block as a function of time. For advanced students, solve this differential equation using separation of variables. This one, I should expect most of you to be able to do this. It's a polynomial equation. And as a polynomial, you should be successful. I don't know if you will be, but you should be. So let's see, I'll put the floor here. And we'll indicate that the floor has some kind of weird, or the box is experiencing some kind of weird drag force. And that drag force opposes motion. So we're talking about a force this way on the box due to drag. And we have a boundary condition that at t equals 0, the velocity equals v naught. That's our boundary condition. So there's only one force in the x direction. It equals ma. So I want to be careful about this because this velocity and my acceleration are in opposite directions. So there are some choices you have to make here. If I want to line up my coordinate system to be in the positive direction for the acceleration, that's fine. That means this has to be negative. Oh well. So question 21. An object of mass m is sliding across a level floor where it is experiencing a drag force that is proportional to the velocity of the block. And it gives me an expression there. So the drag force is proportional to the velocity of the block squared, where k is some constant. There's no frictional force. The speed of the block is v naught at time 0. Alrighty. At t equals 0, v naught equals 0. Or you could write this as v at time 0 equals v naught. I'm sorry, I wrote that wrong. Not v naught equals 0, v equals v naught. There. Or you could just write it like that. Create a differential equation that could be used to determine the velocity of the block as a function of time. For advanced students, I'd say you guys are advanced students. You should be able to go and see it to the end. This is a polynomial function, so I believe you guys should be able to do this. It doesn't require particularly anything advanced, except for what we've already done during kinematics. So you'll have to bear with me. The software, the manufacturer of my software has made a radical update to the software. Everything is different, and I have decided to hate it. So, and it's not that I don't like change. I don't like these changes. So I'm doing my best, but some of the tools are moved or are different. If we assume that the box has a velocity in this direction, then it seems like it hits an area where suddenly it's dealing with a drag force that is attempting to slow it down. Does that make reasonable sense? All right. We have to be careful about the way we deal with direction here in a few minutes, so I don't want to make you nervous. The velocity is squared there. You see that? So we will need to be careful. This might be a case where it might be easier to make the acceleration negative on purpose from the start of the problem. But there's no reason. We can do the problem in any direction we like. It gets a little squirrely, we start dealing with calculus. So I would start by saying, well, there are three forces acting on my object. There's weight, normal force, and the force of drag. And net force equals ma. Now, we're only interested in the drag force. Looks like the force in the y direction are balanced. So I don't think there's much here to do in the y direction, but I think we could say if we wanted to that normal force equals mg. It says level ground, so that's reasonable. But in the x direction, we will have k v squared equals ma. if we make to the left the positive direction. All good? Now, I'm going to make a choice right now, a choice that aids me in the future. I know the drag force is reducing the velocity of the object, right? It opposes the direction of motion. And although to the left is perfectly valid direction to be positive, because I know it's slowing it down, I'm going to go ahead and just make this negative now and not worry about having to make the velocities negative in the future. Is everybody okay with that? It's just a choice I'm making. We could do it in reverse, but we have to carry that to later. So I am going to make the velocity the positive direction for this problem. And therefore, I'm forcing this acceleration to be in the negative direction. It's a choice. And like I said, I get to make the choices. But when you see what we have to do for this problem, you might understand it. I've already talked to you, or at least to this class, about what it takes to make something a differential equation. To make something a differential equation, it has to have a differential in it. And in the case of this problem, we are trying to get velocity as a function of time. You have two differentials in your arsenal. You have acceleration is the rate of change of velocity, which is the differential of v with respect to t. And you have velocity is the differential of position with respect to time. You have these in your arsenal. We've talked about them earlier in the year during kinematics. It is not uncommon to be asked to make a differential equation, and a differential equation requires one of these substitutions, to substitute a differential into our equation. And although we'll learn a couple other derivatives in the future, this is what you have to work with. So creating a differential equation is just replacing one of these variables with its differential form. Now, I'm going a little further today to tell you to look at the future of your problem. You are trying to create an expression of v as a function of t. You'll notice there's no t anywhere in here, right? We are introducing time into the problem by introducing a differential that has t in it. That's what we're trying to do, introduce time into this equation. Now, I could make this substitution, which eliminates velocity in the equation and introduces position in time. Do you see why that might not be the best option? Right? It's also squared, which that's going to be a problem. So for the most part, we use Newton's second law as a place to begin a differential equation. It's a very popular place to do so because it's got acceleration in it. And it is the acceleration that we generally deal with when it comes to the derivative, especially since there are so many forces that are proportional to velocity. This will create a differential equation that introduces t into the equation and also makes our differential based on velocity. That's good too, since velocity is the function that matters here. Now, if we had a force that was somewhat position dependent, and we have some, Hooke's law is position dependent, then we might want to do something different. But this is not position dependent, it's velocity dependent. So by just substituting in dv dt, you have actually completed the part of creating a differential equation. This is a differential equation that could be used to create a function of the velocity with respect to time. Now, what happens next we haven't talked about, but we're going to right now. I'm going to tell you what I expect everybody in the room to be able to do and what I don't expect to be able to do. Because what we're going to do is not hard. It's going to be to take this and put it in a form that can be used to get velocity as a function of time. And it's not much. It's a process called separation of variables. It is one way to solve differential equations, and it's basically chapter 1 in any differential equations book. And then you'll find out that that solves a very, very limited set of differential equations. And so the rest of that differential equations book is going to be about every other possible way of doing it. I have a Diffie-Q book over there. If you're ever interested in seeing some math like that, it's a good idea. Calculus is like multiplication for algebra. Remember you learned all your multiplication rules and such, but then you had to learn algebra and you realized that multiplication was a big deal in algebra because all the stuff that happens there. Well, once you learn all the stuff about derivatives and integrals, those become your standard parts of dealing with differential equations. So it's just the first step, the early steps. There's always more math out there. Separation of variables is what we're going to do. And when you hear me say that, I am telling you that there's a specific set of steps I want you to do. The first step is to separate the derivative. Separate the derivative. You do this by multiplying by the denominator of the differential. And I wouldn't write all these steps out if I didn't think it was important, so keep that in mind. All right, so the differential is dv over dt. I'm going to multiply both sides by dt. My next step is to collect variables. Now what this means is I need to get any appearance of t on the same side as dt, and any appearance of v on the same side as dv. Not particularly hard here. I think you all can see that I don't have a t anywhere, but I do have v squared on one side. Do you guys see that okay? Now what I do next doesn't really matter how I decide to do it. Because it's k times v squared, I could just divide both sides by v squared, and that would be fine. I could divide both sides by kv squared. I could divide both sides by negative kv squared. Doesn't really matter what you take over. I just got to get the v squared over to the other side. It is sometimes it is easier to put all the constants on one side. Do you notice that there are two constants here, k and m? They're constants in that they don't have anything to do with v or t. The mass of the object isn't changing with respect to time, and it's not changing with respect to velocity. And k is not changing with respect to time or velocity. So collect variables. You're trying to clean this up to make it easier for you. I'm going to move the m over to the side with the k just to get the constants all on one side, and I'm going to move the v squared over to the side with dv. So I'll have negative k over m dt equals 1 over v squared dv. Notice, this is just algebra, right? You guys are seeing this, it's just algebra. I haven't done any calculus yet. However, some of the choices here you may not have made. I'm making the choice to put the constants together because they just get in the way anyways. And so having them in the way only on one place is okay. And knowing to put the negative sign or leave it on one side, it doesn't matter. You don't have to do these things. It will still be the same answer. But what I'm going to do next is starting to prepare this for calculus. And so we're going to use a symbol here because we are going to be taking the antiderivative of both sides. And the symbol that is a part of that is the integral symbol. So I'm going to draw the integral symbol on both sides because we're doing more than just taking the antiderivative. We are taking the integral of both sides. And you can take the integral of both sides of an equation. But you still haven't done any calculus. You've just drawn a symbol on the front that says calculus is next. The symbol is an S. It's designed to look like an elongated S because the integral symbol also takes the summation of a function. So rather than using the summation symbol, we use this fancy S. And just like the summation symbol, which has symbology, there's something to put in the bottom and something to put in the top on a summation symbol, your starting point and your ending point. We also must put our starting point and ending point here. This is the last bit of algebra I'll expect you to do. But the next thing you're supposed to do is apply your boundary conditions. And before my math purists attack me for doing it this way, yes, I do know that I can do this as an indefinite integral first. And yes, I do know that that will produce a constant. And yes, I do know I can apply my boundary conditions after the fact to get the value for that constant. And no, I don't want you to do it that way because AP is looking for you to do it this way. So please do it this way. They want to see you apply your boundary conditions in line with your integrals. So do these as what are called definite integrals. Put your boundary conditions here. Now, boundary conditions aren't a big deal. We already have boundary conditions. We are trying to create a function that tells me the future velocity of an object with respect to time. So in the tops of my summation symbol, put a symbol that you will use for each variable for the future value of that variable. That's complicated to say, what symbol do you want to use for time in the future? I'm going to put T. Makes the most sense. And what symbol do you want to use for velocity in the future? For a future velocity, I'm thinking V. V will work just fine, right? I want to create V as a function of T. This is working those variables into the problem. The bottom has to be boundary conditions. Do we know the velocity at some point in time? And we do. We know at time 0, the velocity is V naught. This would have been the moment where we would have had to remember to put negative V in for V naught. But you can see why, it wasn't a big deal. The negative sign is already here. I could have just put it there. We'll get the same answer. But I think it's easier to do it this way. Now is calculus, this moment. And this is where you can all just tap out. I want you to be able to get to here. Was there anything here that was really particularly tough? Just algebra, right? You will be receiving credit on this test if you can create the differential equation. All right? On the next test, you will have to make it all the way to here. On every test thereafter, I will expect that we will have practiced this enough times where you can do the rest. Now, this class should be able to do this one anyways. You should be able to. This is a polynomial. The left side, do you see t? I just see dt. Do you see an expression with t in it in this portion of the function? No, I don't see it there. But the way this works is these are your boundaries telling you to take the integral with respect to t. What's in here is your integrand, the thing that you are finding the antiderivative of. So do I see a t in the integrand? No, but there's an implied t there, t to the 0 power. In the integrand on the other side, do I see a v? Is there a v in that integrand? Well, good, because this side I'm taking the integral with respect to v. Constants, they can just come outside the integral. It's a summation. And since those are a term that will be in every term of your summation, they just get pulled out. So you can just take all of this and put it on the outside. And all this says is take the antiderivative of t to the 0 power. You guys remember how to do that, right? You're supposed to. Just because we're not in that unit anymore doesn't mean that we don't do those things. To take the antiderivative, you add 1 to the exponent and then divide by the new exponent. So this will be t to the 0 plus 1 divided by 0 plus 1. That is the antiderivative of the function. I need to drop my constants down because they were just pulled out front. And I need to remind myself to put in my boundary conditions. That was the calculus on the left side. 1 over v squared is a polynomial, right? It looks more like a polynomial, though, if I write it like v to the negative 2 power. Do you guys remember that? Because we did this one. So add 1 to negative 2. So v to the negative 2 plus 1 divided by my new exponent, negative 2 plus 1. That's the antiderivative. And now I need to remember to evaluate it from v naught to v. All right, that's the only part that's calculus. That's it. There are harder ones. This was just not it. All right, the boundary conditions. This is new as well. You have to put in the top boundary and then subtract what happens when you put in the bottom boundary. So all of this is just t. So put in the top boundary, t, and then subtract and put in the bottom boundary, 0. Done. Let's see. The other one, though, that's -1 over v, right? Because the denominator is -1 and the exponent's -1. So this whole thing is -1 over v. All righty. Put in my top boundary, -1 over v. Subtract and put in my bottom boundary, -1 over v naught. There you go. Well, that was it. That's your answer. However, I would not accept that answer. You wanted v as a function of t. Is this v as a function of t? No, it's not. To get v as a function of t, you will have to get v by itself. It's just algebra. But I don't know if you can do that algebra or not. You should try. It's not hard algebra, but you should try. But since we might want to do other homework questions, I don't know if we should belabor this, as this is just an exercise in algebra. But you should try. All right, I'll leave that. I am afraid that some of you don't know how to do that. I do have concerns. I will say that one thing you could do to mitigate some of this is multiply both sides by -1. That could start making this a little easier for you, right? But still, you have to solve for v. You have to get it by itself. You have to isolate it. I would probably go ahead and add this to both sides, you know, and then, I don't know, get an equation with common denominators so you can invert both sides. That's the way to go. So if anybody wants me to do this, I will. If not, I'll work another homework question. Your call. Yep. Want me to work it?
Yeah.
All right, let's add 1 over v naught to both sides. This is kt over m plus 1 over v naught. Since I have to invert both sides, and I would really not like to have a super complex fraction, because if I just inverted it right now, I would get a super complex fraction, I'm going to get common denominators on the left. Do you guys know to do that? You do now. So my common denominator will be m v naught. And so that will make this k v naught t plus m. Common denominators. All good? You guys see what I've done there? Any questions about that? And that equals 1 over v. So now I will invert both sides. So I'll get v equals m v naught divided by m plus k v naught t. V is a function of t. Interesting thing here, we know something about this problem. We know that at t equals 0, the velocity is v naught. Let's test that. V at time 0 will be m v naught over m plus k v naught times 0. Well, does that turn out to be v naught?
Yeah.
How convenient, since that's what it's supposed to work out to. And do you also know that the limit as t goes to infinity will be that the velocity goes to 0? Do you see that? Because t is in the denominator, so as time gets bigger, the bottom of this fraction gets bigger, and the whole fraction gets smaller. Is that what I expect if there's one force acting on my object and it's to slow the object down? Eventually it'll stop it? Yeah, eventually stops it. Now, if you actually look at this, it decays forever and never actually stops. But that's not reality. Reality is it'll eventually stop. But there we go. That was our algebra. Wow, look at all that algebra. Look at all of that. I am expecting this. Next test, I'll expect you to get down to here. And then every test thereafter, I will expect you to get to here. I think that's a fair progression of your skill set. Everybody understand? All right, what's your question? And it makes an angle with the horizontal of 15 degrees. All good, everybody? All righty. I could do this in terms of symbols, or I can do this with the numbers in place. You asked, so your call. Symbols, sure. So I'm going to use angle theta for the angle, and I'm going to use L for the length. Is that okay? All right. I believe there are two forces acting on the ball. I believe there is a downward force of gravity. And an upward force along the string of tension. Something like that. In order for the ball to travel in a circular path, there must be an acceleration towards the center. So I'm going to make towards the center the positive direction. I'm going to align my coordinate system up with the x direction that will go through the center of the circle. Now, because of that, I'm going to have to break the tension up into two components. So I see a component this way, which I will call T cosine theta, and I see a component this way that I will call T sine theta, because theta will be right there due to alternate interior angles. Still good? I'm not going to skip steps, but I think we can probably all come to this conclusion that T cosine theta equals MAC, and T sine theta equals mg. Now, regardless of what version of acceleration I choose to find, meaning angular or linear, I can probably put these things together and cancel out m and t in one step. That's what I'm going to do. So I will get tan theta on the left equals g over ac on the right. That all good? All right. Regardless of which version of centripetal acceleration I use, I'm going to need R. So you're going to have to pick how to get R, but I think there's some geometry here that I could use. Judging by the way the picture looks, I think that the radius has to be the bottom of that triangle, with the hypotenuse being the length. So I think we can write that the radius is equal to L cosine theta. I think we have all the tools we need to find what we're looking for here. So if I solve this for AC, I'll get g over tangent theta. And if I want to find the linear velocity, then v squared over r equals g over tangent theta. So v squared equals gr over tangent theta, which is gl cosine theta over tangent theta. You don't really get any, gain anything by breaking up the tangent. You'll just get cosine squared in the numerator and sine in the denominator. So, I mean, there's probably some trig function you could work your way out of this, but I don't think, you're just gonna plug in numbers and get a value anyways. So, you can do the same thing to get omega, but they wanted an RPM. So you might be best served just working from here. Remember, velocity equals omega times r. So once you get this velocity, you can just divide by the radius again, and that's going to give you the angular speed, but that angular speed is in radians per second. I believe this gives you a velocity of 6.6 meters per second and an angular speed of 4.4 radians per second. I'm not sure about that one. I'll put a little squiggle up there. I might be wrong. But I think 4.4 radians per second ended up working out to 43 RPM. Something around there. So I use unit multipliers, and that's what I teach when it comes to conversions. If you're not good at converting, I can show you how to do conversions. It's up to you guys. All right. Unless anybody has any objections, I'm going to use this as my conversion as my test bed for conversion. Is that okay? All right. Let's say I have to convert 4.4 radians per second into something else. I'm going to say this, and it's not an insult. Per means divide. So meters per second is meters over seconds. Rotations per minute is rotations over minutes. Just in case you didn't know, the word per means divide. Now, I believe in using unit multipliers because you look really, really, I'll use the word silly, but there are worse words to use that are more appropriate when you come at me saying, oh yeah, I divided by 100 instead of multiplied by 100, because I just didn't know which way to go with that. You look kind of silly doing that. If you know that all you have to do is write this out and you'll always get it right without making a mistake, you look silly when you make a mistake. So I start with what I have, and across the way, I write where I want to go. Right? I'm starting with radians per second, but I want to go to revolutions per minute. I then think to myself, how many things am I going to have to do to get there? For example, do I know a way of converting from radians to revolutions? Do I have a way of converting from seconds to minutes? Now, the reason I said you have to kind of know where you're going, because you might know how to go from seconds to minutes, but you may not know how to go directly from seconds to days. So you might have to go seconds to minutes, minutes to hours, and hours to days. You follow me? So if my thing was revolutions per days, well, then you might have to have more of these multipliers in there. You'll need a multiplier for every change you wish to make. So, but I think I have one change to go from radians to seconds, radians to revolutions, and one change to go from seconds to minutes. So for each change, I'm going to write a fraction. And I think I only have to worry about two changes. Each one of these is going to do a conversion. They're a unit multiplier in that they are not changing the value, they're changing the units. Now, the first thing I have to realize is I have radians in the numerator, and I want to be left with revolutions in the numerator. So to get rid of the radians, I have to put them in the denominator, so they will cancel the ones that are in the numerator. And I want to be left with revolutions, so I put it on the other side. Now I need my conversion fact. Do you have a conversion fact that can get you from radians to revolutions, or from revolutions to radians? Do you know one? 2 pi what? So there are 2 pi radians for every 1 revolution. There it goes. That conversion will convert me now from radians to revolution. Looks like I'm going to be dividing by 2 pi. Let's go to the next one. I want to get rid of seconds. Since they're in the denominator, I put seconds in the numerator. And I want to be left with minutes, and minutes are in the denominator. So there we go. Seconds in the numerator, minutes in the denominator. Do I have a conversion fact that'll help me go from seconds to minutes or minutes to seconds? Yes. There are 60 seconds in every 1 minute. Excellent. Multiply across on the top, multiply across on the bottom, divide, and that's your answer. Do it this way, you'll never get it wrong. The best part about this is this also works for things that are like meters per second squared, in that you can square one of your unit converters if the value is squared. And it helps you for more complex unit conversions. So that's why it's probably a good idea to learn to do this, because it can make some things much easier to do. But all right.